Hi guys, welcome back to Data Every Day. Alright, today we're looking at a dataset of children's books and stories that are highly rated, and each children's book comes with a name, a description, and then an age group, a target age for the book. So what we're going to try to do is use the name and description to predict the age group of a book. So I'm going to get into our notebook here. Given the names and descriptions of highly rated children's books, let's try to predict the age group for a given book. And we will use a TensorFlow neural network with an RNN to make our predictions. So I have some imports here. This is everything we'll be using in the video. NumPy and Pandas. Then we have Plotly Express, just for a bit of visualization. Regular expressions. These are like the pre-processing imports. We get stop words from the Natural Language Toolkit, Tokenizer and pad sequences from keras.preprocessing, and the train test split function from sklearn. And then for our model, we'll use TensorFlow. Let's go ahead and import those, and I'll load in the data using pandas.readcsv, and I can get the file path right over here, childrenstories.csv. Paste that in, take a look at data. Oh, actually, okay. UTF-8 codec can't decode, so what we can do is just go in here and say encoding Latin 1. Alright. Okay, so there's a few things we're going to have to do here. First, we're going to have to figure out what's going on with this label column called cats. Then we're going to have to process the names and description columns into a format that can be understood by the model. So let's start by creating labels. And for this video, I actually have some markdown blocks prepared. I'm just going to paste them in. We can review. So I said we would like to create labels from the cats column. Let us divide the labels in the column into two categories, younger and older. So the reason I say this is because if we take a look at the value counts, you can see we have actually a lot of different entries for this column called cats, I guess for categories. And some of them are, there's only one example, and then some of them we have a number of them. But the problem is there's a lot of like overlap. Like 3 plus, it's very similar to, I mean, like 2 to 4. Okay, let me think of a better example. 3 to 4 and 3 plus. Sort of saying the same thing, right? So what we can do to make it easier is let's just split it into younger and older. So to do that, what we can do is type .sortIndex, and that will sort it by index. You can see we now have the numbers more or less sorted. The only exception here is that the 2-digit numbers are coming a little in between because they start with 1. So we'll just have to factor that in. So what I'm going to try to do here is figure out, okay, what age should we cut it at? I want to try to find an age where these value counts sort of like they're about even. And I mean, you can take a closer look, but I found that if we say 5 and up is older and 4 and below is younger, we get a rough 50% split between the two classes. So right here, I'll just paste in another markdown. It says, looks like 5 and up is a good way to classify older books. Let's just sort the unique values as a list so we can see any leading or trailing white space in the entries. So when we have it in this format, we can't see if like there's a space at the end. So what we can do is just take data subcats.unique. This will display it in a similar format. We can actually see it here though. Interesting. Yeah, it's a little easier to see though if we turn it into a list. Alright, and we can actually sort that list as well with sorted. Now we can see, you can see this, for example, has no value, and doesn't look like there's actually any white space at the end of these, the only one being here. So we want to see how many of these we have, because this is like a null value, right? This is not actually, we don't know if this is old or young. We're going to check. So we can query the dataset, data.query, and we'll check cats equals, and then the value is age with a space at the end, age space. And there's only 2 examples. So in total we have 430 examples. If we drop 2 of them, that'll be okay. So what we're going to do is get the indices from that .index. Will just give us these 2 indices, and then we can say data.drop those indices from axis 0. And anytime we drop rows, we want to reset the index afterwards. So, and I include drop equals true to avoid having the old indices as a new column. So that's data, and I'll run that, and then I also just want to put in some more markdowns. Figure this is better for the notebook. So as we can see, there's one blank age, so let's remove any rows with this value. That's what we did. And now we're going to create a list of all the values that count as younger. So this I'm just going to paste in because it took me a while just to get this. Basically what I did was I copied all the values up until 4 to 8, and anything that had 5 or past as the starting age we will count as older. So right here I have the young ages. Notice I took out all these 2-digit ones because those are older, and I also included the 6 months because that's younger as well. So here are our younger ages. So anything that has this is going to be considered young. So let's run that, and then we apply a lambda function to change the value for a given book in the cats column to 0 if the book is for younger children, and 1 if the book is for older children. So we'll take data sub cats, and that just looks like this, right? We're going to apply a lambda function that's going to take an age. So an age would be something like this, and it's going to return 0. It's going to change it to 0 if age is in young ages. So if this value is in our list, we'll make it 0, and otherwise it'll be 1. So at the end of this, we'll have a column of 0s and 1s instead of a column of all these different mixed values. 0 will denote younger, and 1 will denote older. So I will make this the new cats column, and now let us check the split. Let's see how well we did. So we can divide the value counts by the total number of examples to see the split of the classes. So data sub cats dot value counts looks like this. It looks pretty even, but we can get it in a percentage form by dividing by the length of data sub cats. And it's a 51 to 48 split. So 49 really. That's pretty good. Alright, we could probably get it to 50-50 exactly, but this is very good. I don't think we'll have to adjust it. So now we actually have a label column. If we look at data, we now have 0s and 1s in this place. So why don't we start processing text? So this is the next step, which is let's take names and descriptions and let's turn it into machine readable form. Alright. So now that we have the labels properly assigned, let's prepare to create a dense encoding of each word in the name and the description. So note I'm making a dense encoding of each word. So what that means is I'm going to assign each word to a unique integer and then encode each unique integer as a dense vector. And we'll do that within the model. We'll have the Keras embedding layer actually learn the representations of each word. So we can start by defining a function to remove any digits and stop words from the texts. So we'll create this function, process text, takes in a text, which would be either a name or a description. And we'll start by removing digits. So I imported RE, or regular expressions. So we can take our text and set it equal to re.sub, which is basically substitutes a regular expression, or it substitutes text captured by a regular expression with another string. So we'll include the regular expression here, and the regular expression we want to capture is any digit characters. So \d will capture a digit character, and plus will do it any times from 1 to unlimited. So basically it's saying anytime you see a digit character and then any number of them in a row, we will take that and we will replace it with a space. And so that will just effectively remove any digits. We also want to apply that to text, and so that will do what we need. Then we will split on white space. So simply text equals text.split. And the reason we split on white space is because now it's in a list form, and we can then join on white space, but only the words that are not stop words. So stop words are basically just the most common words in a given language, and they don't contribute much to NLP tasks in terms of the information they carry. For example, it is probably a stop word. We can actually check them. We imported stop words from nltk.corpus, stopwords.words, and then we pass in a language, English. You can see there's a list of all the stop words in English. So these are words that don't help the model. In fact, they may slow it down, make it more difficult. So the word I, me, my, myself, etc. These are just the most common words. And you can see it is actually in there. So when we run this, it should remove it, along with a bunch of others. So this function is just going to remove digits and stop words, essentially. So text is going to be, we're going to join on white space. So we're saying join on a space character. And what we're going to join is not actually text, which would work, but it's going to be a list comprehension of words within text. And that's word for word in text if word not in stop words. So stopwords.words English. So we're splitting it into a list, and then we're joining it back together, but removing any stop words in the process. Alright, and that will do it. So return text. Here's our function. And let's create 3 variables, names and descriptions, which will be the processed text columns, and labels, which will just be a copy of the cats column. So names, right, is going to be data sub, names dot apply process text. So this will apply process text element-wise to each name in the column, and then store it in this new names, which I assume will be a pandas series. Then descriptions is very similar. Data sub, I think it's called desk. Yeah, desk.apply process text. All right, and then our labels will just be a copy of the cats column as it is, because it's already 0 and 1. So dot copy. And why don't I just make copies of these as well? So dot copy, dot copy. All right, we'll run that. Let's just take a look at some of these descriptions. and labels. Alright, so here are the names. Looks like, let's see, I'm not sure if we can see any stop words that were removed here. Oh yeah, here's one. This is a memoir of love and loss. It became a memoir love loss. So of and the have been removed. And then these are the descriptions, very similar. We can also see there was a 72 here, and it has been removed as well. So digits and stop words are gone from both the names and descriptions, and we've stored them in these new variables. Alright, and then we have the labels, which is just zeros and ones, and they all match up to each other on indices. Okay. Now let us tokenize the texts to give us a word to integer mapping for all the words in all the texts. So Keris's tokenizer will automatically apply filtering for punctuation, I should say /special characters, and split the strings into words on whitespace. So let me break that down a little. We're going to create this tokenizer. That's a tokenizer object from Keris.preprocessing. And basically, tokenizer is going to look through a string that we give it, and it's going to split it on whitespace. We could also pass it a list if we wanted, but we're doing strings here. So it's going to take each word, and then it's going to process the word. It's going to run it through a series of filters. We can actually see, if we look up the on the Keris documentation, we find the tokenizer class. You can see it has these filters that it's going to remove any characters that lie in this filters. Now we could specify our own if we wanted, but this is fine. It also sets it lowercase and splits it on whitespace. In the end, we will have sort of like a more processed words that we will then tokenize. By tokenize, I mean take a unique word and map it to a unique integer. Okay, so we'll fit the tokenizer, tokenizer.fit on text, and we're not just going to fit it to one of the names or descriptions. We want all the words to be considered, everything in names and everything in descriptions. So I'm going to fit it on the concatenation of the two. Pandas.concat names descriptions. So those are two pandas series, so it's we can just stack them on top of each other and then consider all the words within the concatenated series. The names is going to be tokenizer.text to sequences. So this is just like a transform function that's going to transform all the words in names based on the fit that we have provided it. So names is no longer going to look like this. It's now going to look like a series of integers, where so each name will be a sequence. In this case, it would be 3 integers, one for hide, one for and, one for seek. This would also be 3 integers, 4 integers, etc. And then we'll do a very similar thing for descriptions, except we'll just transform descriptions. Alright, so let me just demonstrate a little. Now our texts look like sequences of integers. So if I look at the first 5 values in names, you can see we now have sequences of unique integers where each integer references a word. And we can get the size of the vocabulary by checking the word index in the tokenizer. So tokenizer.wordIndex looks like this. It's basically all the most common words in our vocabulary. It's all the words in our vocabulary, but ranked in terms of frequency. So the is the most common word, that's why it's been assigned 1. Book is the second most common word, so it's been assigned 2. Story is the third most common word, etc. Notice there's no word assigned to 0. So if we want the total size of the vocabulary, we want to get the length of tokenizer.wordIndex, but +1 for 0. And the reason I do the +1 is because when we pad our sequences, so what that means is you can see currently we have sequences of variable length. We want all of our sequences to have the same length, so what we'll do is we'll just add a bunch of zeros at the end to make sure they all have the same length. And we use 0 to pad it. So that's why we have this +1 to also include the 0 character. So that's going to be our vocab length. And we're going to need this in order to train the embedding layer. So, yeah, let me paste this in. Let's get the size of the vocabulary, the number of all unique words across all texts. We can get this from the length of the tokenizer's word index and add +1 for the 0 character, which is not assigned to any word, but instead used for padding. So, yeah, we'll print it out when we're done. The vocabulary length is 7,269. We should also get the lengths of the longest sequences in names and descriptions. So we want to know how to pad these sequences. So descriptions look similar if we want to look at it. It's just they're a lot longer of sequences, as you can see. This is one sequence. All right. So let's get the maximum sequence length for the names and the maximum sequence length for the descriptions. So note that if I have names, it looks like this, right? There's a bunch of sequences, each one for a new name. If we apply a lambda function to that, that takes in a name and spits back the length of the name. Oh, it's a list? Oh, right, it has become a list. Okay, we can't use .apply. Instead, we'll use map. We'll map this function to names, and then turn that into a list. Now you can see each sequence has become the length of the respective sequence. So 3, 3, 3, 4, 4, 2. Up here, it's 3, length 3, length 3, length 3, length 4, length 4, and next one would be length 2. So these are the lengths of each sequence. And if we just take the maximum of that, numpy.max, we get the longest sequence in our names. So the longest sequence has 9 words. So I'll call this max name length. And then I'm going to do the same thing for the descriptions. I'll call this max desk length. And we're going to do this to each description in descriptions. Okay, and we can print the results when we're done. So the max name length is 9. The max description length is 171. Fantastic. We can now pad the sequences according to their longest sequence. Any sequences shorter than the max will have zeros added to the end. So names looks like this, and we want all of them to be of length 9, right? Because that's the longest sequence in here. So we're basically going to add zeros to each sequence until each sequence has length 9. And we can use pad sequences, which I imported from carousel preprocessing.sequence, which will pad names, which is this, and this will be the new names. And then let's specify the max length, which will be max name length. That's just 9, right? And we'll also say padding equals post. So by default, it'll add the zeros at the beginning, but if we specify post, it'll add the zeros at the end. And I don't think it makes much difference. I like it better at the end. We'll do the same thing for descriptions. So descriptions equals pad sequences, descriptions, and then the max length here will be max desk length, and we'll also have padding post. Alright, we run this, and we can say now names and descriptions are proper NumPy arrays that have sequences of uniform length. So why don't we print out the shapes of each and just take a look at them. So names looks like this. We have a shape of 428 by 9. So there's 428 examples, and each sequence is of length 9. For descriptions, we have also 428 examples, but each sequence is of length 171. So these will be our inputs to our model. We are ready to start working towards training. So we will start splitting the data into train, test. All right, we can split the data. We can split into train and test sets using sklearn's train test split function. Let's use a training size of 70% and include a random state of 100. So a random state just ensures that we can get reproducible results. So we have names, descriptions, and labels, and we want to split them at the same level so that all the indices still match. That's why this function is so useful, because not only does it split them, but it also shuffles the data. So train, test, split, names, descriptions, labels. Let's include a train size of 70% and a random state of 100. And then I'm going to assign this to 6 new variables, which will be, so it's going to be names train, names test, then descriptions train, descriptions test, then labels train, labels test. Alright, and we have these 6 new variables as our train and test sets. Alright, and with that we are ready to model. So we're going to feed our feature data in through 2 inputs, one for the names and one for the descriptions. So I'll just paste this in. First, let's focus on the names. We can embed the names in a high-dimensional vector space using a Keras embedding layer. This can allow us to learn representations for words rather than manually creating the representations. It also allows us to have smaller inputs as we are using a dense encoding. So we could do it manually, right? We could encode each word as a sparse vector, which means really a one-hot vector. You could think of a vector of length, vocab length, which I think, what was it, 7,269, where each location, each element in the vector corresponds to a word, and we'll have all zeros except for one, which would be the word for the given example. But that means each word vector would be 7,269 elements long, which is just a lot, and it's a lot of useless space. There are some cases where you'd like a sparse encoding, but for this application, a dense encoding would be a lot better. Which a dense encoding is saying, okay, let's imagine a vector space of some dimension of our choosing, and then if we wanted to encode each word as sort of like a location in the vector space, or as a unique vector in the vector space, then we would only need as many elements as there are dimensions in the vector space to encode each word, if that makes sense. So let's say we pick a 64-dimensional vector space. Each vector, or each word, requires 64 elements to express it as a vector, whereas before we needed 7,200 and something elements to express it. So yeah, it allows us to have smaller inputs, and it also allows us to learn representations. So where to actually send the words in the vector space is learned by the model. So fantastic. We will then flatten the output from the embedding and prepare to send it to the final output. So let's create an input. Name input is going to be tf.keras.input, and the shape is going to be a vector of length max name length. Alright, we'll give it a name as well, name input. So that's our input layer, and we're sending in a vector of max name length. So that is actually 9, right? So each one of these is going to be an input into our model. Then we're going to create an embedding layer, which will be tf.keras.layers.embedding. And embedding layer will take 3 arguments. Input dimension, which will be embedding layer basically takes those sparse representations of the words and sends them to a dense representation of the words. So the input is going to be the dimension of our vocab length, of our vocabulary space, you could think of. So it's vocab length. This is saying take a one-hot vector, essentially, which is 7,269, was it? Yeah. And we're going to send it to our output dimension, which is just whatever we like. I picked 64, but we could experiment with this. And so that's saying take, here, why don't I include that up here, actually. Name, how about name dimension, 64. And we could put name dimension here. So we're going to send it from 7,269 dimensional space to 64 dimensional space. And then we will have an input length. This is just going to be the shape of our vector, of our sequence, right? So that would be max name length. Alright, so this is the shape of the incoming word, this is the shape of the output, and this is the length of each sequence. And yeah, we'll give that a name as well. Let's call it name embedding. And we'll pass in name input. Alright, then we're going to flatten the output from the embedding and prepare to send it to the final output. So I'll create a flatten layer, I'll name flatten. This will just take all of our word embeddings for all the sequences and flatten it into a single one-dimensional vector. So tf.keras.layers.flatten. Name will be name flatten, name embedding. So we're just going to send in the name embedding output into name flatten. Alright, and we're going to pause it there, so that worked. Before we continue, now let's focus on the descriptions. So these inputs are sort of happening in parallel, and then they converge and send an output. So for the descriptions, we will also perform an embedding, but we will then feed it through a Gated Recurrent Unit, or GRU, in order to capture time-dependent information in the data. So a GRU is a form of long short-term memory model, which is a recurrent neural network. And essentially, it feeds in each word, but also the previous word. So it has a sense of memory, and it's good at capturing time-dependent information in the data. Okay, and we're going to set return sequences to true in the GRU, which basically, if we have it as false, it will return the final hidden state. So I'm not going to go too far into what a hidden state is, but basically we take a word and we convert it, we use weights to send it to a hidden state in the GRU, which will then be passed through itself in a loop, and after each time step, the hidden state will get updated. If we have return sequences as false, it will only send the final hidden state as output. But if we have return sequences as true, it will send all the hidden states from all the time steps. And so, because we're having return sequences as true, which just gives us more information, to be honest, that means we're going to have to flatten it at the end so that we can get one final output. So let's do that. So I'm going to create a desk dimension. Let's also make it 64. And that's because we're also going to embed the descriptions. And this will make this desk input. tf.keras.input. Yeah, it's really the same as this. I'll just copy that and modify it. So instead of max name length, it's desk, max desk length, and the name can be desk input. Okay, then we'll create a desk embedding, description embedding. So I'll just tweak this a bit. The input is the same, input dimension is the same, output dimension will be desk dimension, which just happens to be 64 also. And the input length is going to be the max desk length. And the name is going to be desk embedding. And we'll pass in desk input. Okay, then we'll flatten it. Actually, sorry, then we'll have the GRU. So I'll call it a GRU layer. This is going to be tf.keras.layers.gru. And so the GRU has a number of units, which is basically just the size of the hidden state. 256 works well. Then we will turn on return sequences so that we get all the outputs from all the different time steps. And we'll give it a name, GRU, the GRU layer. And we'll pass in the output from desk embedding. Okay, then like I said, because equals true. Because we enabled return sequences, we're going to have to flatten the output. So call it desk flatten equals tf.keras.layers.flatten, give it a name, and we'll pass in the output from the GRU layer. Okay, there we go. We now have two submodels, and we will finalize our model by concatenating the outputs from the two submodels and creating a final prediction. So this is as simple as saying concat equals tf.keras.layers.concatenate name flatten and desk flatten. So remember, after we flatten them, they're just single vectors, so we can literally just concatenate them. Here's name flatten, the output from from the names, and here's desk flatten, the output from descriptions, and we'll concatenate them together into a single vector. And then we will have our output, which is tf.keras.layers.dense, and it's going to return one value with an activation of sigmoid, so that this one value is a probability estimate for the positive class, which is if the children's book is older. And then we'll give that a name as well. Now let's give the concatenation layer a name. Concatenate. Alright, and we'll pass in concat here. And our model is almost finished. So let's take a look at what the model looks like. Model is going to be tf.keras.model. We'll specify the inputs. We have two inputs here. One is going to be name input, one's desk input. And our outputs is just going to be this final output. Okay, we have our model. Let's print a summary of the model. So this will give us information about the parameters. And then we'll also plot the model. So we can use tf.keras.utils.plotModel to plot the model in a nice graphical way. So yeah, so here's the summary. You can see we have 1,200,000 trainable parameters, mainly in the embedding layers, the GRU layer, and the final dense layer. Then this is the way our model looks. So we have two inputs. One is for the descriptions. So there I have desk there. that gets embedded, it's passed through the GRU, gets flattened. Then one is for the names, comes in, gets embedded, just gets flattened. And then we concatenate the results together and output it to a single probability prediction. Okay, so let us start training. So now we just have to compile and fit our model. Alright, so let's create a batch size. How about 32? Number of epochs. I was running this, it starts to overfit after about 14. We get the best results around 14 epochs. We'll compile the model with an atom optimizer. For loss, we'll use binary cross entropy since we have only 2 classes. And for metrics, let's include accuracy and also the area under the ROC curve. tf.keras.metrics.auc. Name is AUC. This will just give us an idea if our model is performing too well in one category. Although we have a pretty decent split, about 50-50 split between our classes, so this is not entirely necessary, but it's nice to have. So then we will train our model. We'll store its results in history, model.fit, and so we pass in 2 inputs. If you remember, we split the names and descriptions into names train, names test, descriptions train, descriptions test. So the inputs here is going to be names train, descriptions train, and our true values, true y values, will be labels train. Then we'll give it a validation split, 20%. Batch size and epochs as we specified above. And we'll include a callback function that makes the model run more smoothly from what I found. tf.keras.callbacks.reduce learning rate on plateau. This will just help our model converge. Alright, let's run that. And we can plot the results. So I imported Plotly at the top. You can create a new Plotly plot with px for Plotly express .line, and we're going to draw values from history.history. Our y, which is what we're going to plot on the y-axis, is the loss, and validation loss, and we'll include some labels. How about x will be epoch, and y will be loss. Then fig.plot. What? Not plot. Show. Okay. Maybe I'll give it a title as well. Loss over time. I want to do the same thing for accuracy as well. So call this accuracy, and the values we want are accuracy and validation accuracy. And this will be accuracy over time. Alright, let's take a look. Oh, what happened? Oh, there should be a dictionary. Alright. Okay. So, interesting. It looks like we may have to train for a few, not as many epochs. Possibly. It looks like our validation accuracy peaks around 8 epochs, and our loss was also at a low at 8 epochs. So why don't we try retraining for 8? And we can speed this up a lot by enabling GPU acceleration. but we'll just have to rerun the notebook. Okay, I'll just get the results done here while we wait. I'll run results. I'll store the results in model.evaluate. So we're going to evaluate it on the test set. So names test and descriptions test is going to be our input test, and our output will be labels test. You can see how much faster that trained with GPU acceleration. Okay, so it looks like maybe it's a bit too stochastic. This is not as high as it was before. I think let's set it back to 14. So I can just run after this, run after to retrain our model. And okay, pretty good, pretty good. Let's take a look. So our results are pretty decent. Yeah, actually these are as good as I was able to get. Let's also just print it more nicely. So we have an accuracy of 85% and an AUC of 0.88. So look at this. I wonder if there's a way to get this up. Now, I didn't really I experimented a lot with changing like adding callbacks and changing the epochs, but I didn't really consider changing these values. So let's see if we try increasing the dimension of embedding. See if that will improve our performance. I don't know if it will. Let's just see if it does. So I'll run after. Let me take a little longer to train. Not too bad. And I don't know if this will make it better or worse. But also, interesting. Looks like it made it worse. Okay. You know, I'm not going to spend too much time messing around with this. I'll keep it at 64 for now. But if you guys want to hop into the notebook and mess around, maybe you'll find a better way to improve the model. I'm not sure. But I guess that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. Thanks again for watching. I'll see you guys tomorrow. Have a fantastic day.